Okay, so some more rationalizing, looking at some more examples. Rationalize, assume all variables represent positive real numbers. So whether the directions say divide or rationalize, you're still looking for, making sure that if you have radicals, with fractions, you want to be making sure that you are satisfying all three of those conditions that we talked about. So, square root of 80 over 3n to the 10th. This 80 over 3 I cannot reduce, so it's not serving me any purpose having it combined. So I'm going to go ahead and break it apart into the square root of 80 over the square root of 3n to the 10th. Okay, looking at the radicants that I have, 3 is not divisible by a perfect square, but n to the 10th, and if ever the power is greater than or equal to the index, you can reduce or simplify. Same thing here, 80 is divisible by a perfect square. It's divisible by 16. So we can simplify if we want. Looking at that, so breaking that into the square root of 16 times the square root of 5, we do get that the square root of 80 simplifies to 4 root 5. The square root of 3n to the 10th, 3 is not divisible, so I'm going to have to break this into 2, and n to the 10th is a perfect square. The square root of 3 I can't do anything with, so the simplification here is just n to the 5th root 3. So I've simplified my radicals. I can't do anything in terms of simplification of the fraction, but I know I can't leave it like this because I still have a root in the bottom. So anytime you end up, in this case, it is going to be necessary to rationalize. And so, in terms of rationalizing, I have to multiply. So let's write that. So now we need to rationalize. Okay? And so I'm going to rewrite this. I'm just doing this for your notes so you can see the different steps that we took. So to rationalize, we're going to multiply top and bottom by some square root, and because this is a square root, I'm going to multiply by a square root so that the product of these two is a perfect square. If I multiply 3 by itself, I will get a perfect square. So if I do 3 times 3, that's 9, which is a perfect square. So I know that that's going to do it for me. So I have 4 root 15 over n to the 5th times the square root of 9. Okay, last step, make sure all roots are simplified. So the square root of 9 is 3. 15 is only divisible by 1, 3, 5, and 15. None of those are perfect squares, so I cannot do anything with that. So I have 4 root 15 over n to the 5th times 3 is traditionally written as 3n to the 5th. Okay, so looking at my fraction, have I met all three conditions? Yes, all of my roots are simplified. My fraction is simplified, and I have no roots in the bottom. So now I can stop. Okay, always remember, you can stop when those three conditions are met. This next example, it's kind of ugly, and I'm gonna go through a couple different methods. So, you might want to get out an extra piece of paper for this. But, if we're going through as we have been, looking at this, we would say, okay, as a single fraction, there's nothing that I can do. So I'm going to go ahead and break it apart. And I'm going to come over here so I have lots of room. So I'm going to split this into the cubed root of 2, and please note this is a cubed root now, not a square root. The cubed root of 2x to the 10th over the cubed root of 7y to the 16th v to the 22nd. And, looking at my numbers, 2 and 7, those aren't divisible by perfect cubes, but my x to the 10th, all of these powers are greater than the index, so I know I can simplify. So if we want to do, this is kind of the route we've been taking, doing our simplification. So we're looking for, in this case, not perfect squares, but perfect cube factors. So we're going to have to break this up. 2 is not divisible by any perfect cube, so we'll just keep the 2 here. X to the 10th is not a perfect cube, so when we're talking about variable expressions, we're looking for perfect cubes. Oops, and I need to make sure I've got cubed roots, not square roots. If I don't put any index on there, I'm saying that those are square roots, which they are not. So I'm looking for powers that are divisible by 3, right? When we're dealing with cubed roots, we're looking for powers that are divisible by 3. So that would be 9. 9 would be the largest perfect cube factor of x to the 10th. And our x to the 9th times x would give us our x to the 10th. So let's just finish this out before we go to the bottom. So the cubed root of x to the 9th, that's x to the 3rd. So we have x to the 3rd times the cubed root of 2x. Moving on to our denominator, again 7, so we're going to have to split this up. So product of 2 cubed roots. 7 isn't divisible by any perfect cube, so I'll leave that here. I'll put that there. Y to the 16th is not a perfect cube, but y to the 15th is, because 15 is divisible by 3. So I'll do y to the 15th here, and my remaining y there. Z to the 22nd is not either a perfect cube, but z to the 21st is. So z to the 21st times z. Again, if the power is divisible by 3, it's a perfect cube. So doing our simplification, the cubed root of y to the 15th is y to the 5th, and the cubed root of z to the 21st is z to the 7th. So we have y to the 5th, z to the 7th, times the cubed root of 7yz. Okay? So, in terms of simplification, we've done everything that we can do. We've simplified our radicals. There's nothing we can do, no common factors between either the coefficients or the radicands that we can cancel. We can't simplify the fraction at all. But we can't stop because we still have this root in the bottom. So because of that, we do have to rationalize. And so before we were dealing with square roots, so let's hang on, before we do that, so now we need to rationalize. Okay, so I'm going to bring this down here. So we have x to the 3rd times the cubed root of 2x over y to the 5th, z to the 7th times the cubed root of 7yz. Okay? So, before, like I was saying, before when we wanted to rationalize, we multiplied by square roots because we had square roots. Here we've got a cubed root, so we need to multiply by a cubed root. Okay? Also before, we were interested in getting for the product of these two to be perfect squares, but in this case, since we're dealing with cubed roots, we want the product of these to be perfect cubes. Let's write that down. Okay? We want to choose this so that when I multiply those two radicands together, I get a perfect cube. Okay? We choose the radicand so that when we multiply, we will have a perfect cube. Okay? So, if I'm thinking about, before we said, well, if we multiply something by itself, we'll get a perfect square. With perfect cubes, a number is a perfect cube if it's the product of any number multiplied 3 times. So here I've got a 7. I know that if I multiply by 2 more 7s, 7 times 7 times 7, that number would be a perfect cube, right? So if I multiply by 2 more 7s, I'll end up with a perfect cube. Same thing with my y. I've got 1y here. If I multiply by 2 more y's, then I'll have y to the third, which is a perfect cube, right? So y squared. Same thing with my z. If I multiply by 2 more z's, I'll end up with a perfect cube. So multiply, and again, when you're rationalizing, you're making an equivalent fraction. So whatever you multiply in the bottom to get your perfect cube, you have to multiply in the top as well so that you create an equivalent fraction. So that's 7 squared, y squared, z squared. So in the numerator, we have x to the third times the cubed root of, so if I multiply 2 by 7 squared is 49, so 2 times 49, that's 98. And then I have my x, y squared, z squared. In the denominator, I have y to the fifth, z to the seventh, times the cubed root of, so 7 times 49 is 343, but that's a perfect cube, right? Y times y squared is y to the third, and z times z squared is z to the third. So again, the purpose of rationalizing is so that you can simplify so you have no root in the denominator. This simplifies. We can evaluate it. 343 is a perfect cube. The cubed root of 343 is 7. That's a perfect cube. Cube root of y to the third is y. Cube root of z to the third is z. So this is simply 7yz. Okay? No more root in the denominator. So we have 7 y to the sixth, right? Y to the fifth times y is y to the sixth. Z to the seventh times z is z to the eighth. Here, all of these powers are less than the index, so I know I can't simplify there. 98 is not divisible by any perfect cube. Your perfect cubes are 1, well, other than 1, 8. 2 to the third is 8. 98 does not go into 98. 3 to the third is 27. 98 is not divisible by 27. 4 to the third is 64, and now we're already starting to get too big. So I know that I cannot simplify this cube root at all. So I leave the numerator as is. It's completely simplified. And the question is, can I stop? Am I done? So thinking about our 3 conditions, all of our roots are simplified. Second condition, fraction itself is simplified. There's nothing we can do to cancel with our coefficients, so we're good. And no root in the bottom. So we have met all 3 of those conditions. So now we can stop. So like I said, that's kind of ugly, and sometimes, like in this case, if it were me, I would not have chosen to simplify first and then rationalize. A lot of times if I'm looking at something and I realize that I'm going to have to rationalize. So when I'm at this stage here, due to the fact that the denominator is not all, I don't have all perfect cubes, I know that regardless of any simplification I do, I'm still going to have to rationalize. So oftentimes for me, if I realize that I'm going to have to rationalize, I usually like to do that before I would consider this occasionally to be a waste of time. Okay? If it works for you, then do it. It's not a big deal. But let me show you, if this were me, this is what I would do. Okay? So going back to the beginning. Like I said, this is just if this is me doing this. So I would start doing the same thing, splitting it in to the cube root of 2x to the 10th over the cubed root of 7y to the 16th z to the 22nd. So recognizing that regardless of any simplification, I'm still going to have to rationalize, I often start with the rationalizing. So I'm going to multiply by some cubed root, and again, both numerator and denominator by the same thing to create an equivalent fraction. And it's still the same notion. I know that when I rationalize, what I want is a perfect cube radicand so that I can evaluate with no root in the bottom. So still, I want the product of these. I want this product to be a perfect cube. Okay, so same idea. I have a 7 here. If I multiply by 2 more 7s, I'm going to have a perfect cube. So I'd still pick the 7 squared in this case. Y to the 16th is not. If I and you can multiply by 2 more y to the 16th, so you're just going to have a lot of craziness to do. That works as well. But if you think in terms of smaller values, easier stuff to reduce, y to the 16th is not. If you multiply by 1 more y, then 16 plus 1, that would be y to the 17th, which is not a perfect cube. Remember, to be a perfect cube, it has to end up being something with a power that's divisible by 3. So if I multiply this by y squared, it is going to be a perfect cube because 16 plus 2 is 18, and 18 is divisible by 3. Similarly, z to the 22nd is not a perfect cube. If I multiply by just one z, then that would be z to the 23rd. That's not a perfect cube. If I multiply by 2 z's, 22 plus 2 is 24. 24 is divisible by 3, so z to the 24th is a perfect cube. So that's how I go about. I try to get it so that I end up with, the product needs to be a perfect cube. And so my powers need to end up being numbers that are divisible by 3. So multiplying here, multiplying that by the same thing, what I have is the cubed root of, in the numerator, 2, oops, sorry, not 2, let me erase that. So 2 times 7 squared, 7 squared is 49, again 2 times 49 is 98. X to the 10th, y squared, z squared, over my denominator, which is the cubed root of 343, right? 7 times 7 squared is 343. Y to the 16th times y to the 2nd is y to the 18th. And z to the 24th, when I do z to the 22nd times z squared. And I cannot stop because I have simplification to do, and I saw that root in the bottom. So the cubed root of 343 is 7. The cubed root of y to the 18th is y to the 6th. The cubed root of z to the 24th is z to the 8th. In the numerator, I know I can simplify because I have, this 10 is a number that's greater than 3, so I know I can do my simplification. The other factors will have to stay. 98 is not divisible by a perfect cube, and those are not either. Those powers are less. So I just kind of like to take that and just separate it by itself. So the largest perfect cube that goes into the x to the 10th is x to the 9th. And so that would be x to the 3rd times the cube root of x. So doing my simplification, I have x to the 3rd times the cube root of, oops, sorry, that's kind of, so I've got my 98, I've got my 1x, and then my y squared, z squared. And so this is now fully simplified. And you see, using this method, we get the same thing that we had before, doing the whole big, simplify first, but it really was a lot less work. So it's really just going to be a personal opinion whether or not you like to kind of mess around with all of this bigger stuff or not, and you can do it either way. And the last thing that we need to talk about, whoops, got that there. The last thing we need to talk about in terms of rationalizing, everything that we've been dealing with so far is rationalizing when we just have a single term in the denominator. We don't have any plus additions or subtractions. The next thing that we're going to talk about is how we can rationalize if the denominator has two terms, if it's a binomial. And what you're going to need to do in order to rationalize if you have a binomial in the denominator is to multiply by its conjugate. Okay, the conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b. So when you have a binomial, you have to basically multiply by this another binomial, and I'll show you how it all works, so that basically it's just the middle sign that's different. Okay, so looking at what we have here, we've got 10 over the square root of 20 plus the square root of 2. And we need to rationalize. Those three conditions are still going to be, we're still going to need to meet those three conditions. Our end result, anytime you've got, radical with fractions, it has to be your end result is a simplified fraction, simplified roots, no roots in the bottom. Okay? If you have roots in the bottom and you have a binomial in the bottom, the way that you rationalize, the way you get rid of those is to multiply by the conjugate. Okay, the conjugate of this is square root of 20 minus the square root of 2. Okay, let's write that down. So the conjugate of square root of 20 plus the square root of 2 is the square root of 20 minus the square root of 2. And that is what we are going to multiply by to get rid of our roots in the denominator, to rationalize. Okay? Same idea still applies. When we are rationalizing, we're creating an equivalent fraction. So if we're multiplying the denominator by the square root of 20 minus the square root of 2, we must also multiply the numerator by the same so that we create an equivalent fraction. Okay? Doing these multiplications to simplify. So in the numerator, I just have a monomial times a binomial, so I'm going to have to distribute that 10. I'm going to do the 10 times the root 20 and the 10 times the root 2. So I will have 10 root 20 minus 10 root 2 in the numerator. In the denominator, I have a binomial times a binomial, so I have to FOIL. So the square root of 20 times the square root of 20 is the square root of 400. The square root of 20 times negative root 2, I have minus the square root of 40. Root 2 times root 20, I have plus the square root of 40. And then root 2 times negative root 2, I have minus the square root of 4. before we continue, I want to talk about why this works. Okay, so looking at what we have after we've multiplied this binomial by its conjugate, I have this. Okay, root 20 times root 20 is the square root of 400, which is a perfect square. Root 2 times root 2, root 4, that's a perfect square. Inner plus outer, because I am multiplying with those opposite signs, I'm always going to get opposites, which add to 0. So the benefit of multiplying by a conjugate is, if you have a square root and you multiply by itself, you're going to get a perfect square. Okay? So, and a perfect square is going to simplify so that there is no radical. Also, doing the conjugate allows us to always get opposites for inner and outer, which add to 0. So doing our simplification, the square root of 400, that's 20. And the square root of 4, that is 2. Okay, so in the denominator, those added to 0, so we've got 20 minus 2, our denominator is 18. Again, we need to make sure that we are, once we're doing our rationalizing, we also have to simplify all of our roots and simplify the fraction if need be. 20 is divisible by a perfect square, so the square root of 20 I can simplify. 20 is divisible by 4, the perfect square 4, so I'm going to break this into the square root of 4 times the square root of 5, which is 2 root 5. And so this first term, we've got 10 times 2 root 5, so that's going to be 20 root 5. And nothing I can do to simplify. 2 is not divisible by a perfect square other than 1, so I can't do anything there. Okay? So our three conditions are all of our radicals have to be simplified, which they are. 5 and 2 aren't divisible by a perfect square. No root in the bottom, which we don't have. And the last thing is also that the fraction itself has to be simplified. When you are dealing with fractions and you have multiple terms, the fraction can be simplified if, only if, every single coefficient has a common factor. Okay? So if just these two had a common factor, or if just these two had a common factor, I would not be able to reduce. It has to be that every single coefficient, when you're dealing with multiple terms in either the numerator, denominator, or both, it has to be that all of your coefficients have a common factor. 20, 10, and 18 are all divisible by 2, so we can reduce. 20 divided by 2 is 10. 10 divided by 2 is 5. 18 divided by 2 is 9. So we have now 10 root 5 minus 5 root 2 all divided by 9. So now we can stop. We have the fraction reduced, we have the radicals reduced, and we have no root in the bottom. So this fraction is in the appropriate form. Okay? One more. So we've got the square root of 12 minus 9 root 10 all over 6 root 3 minus 4. Okay? We do need to rationalize because we have roots in the bottom. And so the conjugate of 6 root 3 minus 4 is 6 root 3 plus 4. So to rationalize, we're going to multiply by 6 root 3 plus 4. Again, when we rationalize, we're writing an equivalent fraction. So we have to multiply the numerator by that same value in order to write an equivalent fraction. We've got a lot of work ahead of us because we have a binomial times a binomial in the top and a binomial times a binomial in the denominator. Okay, so we have to FOIL in both numerator and denominator. So I'm going to give myself a lot of room here. Square root of 12 times 6 root 3. So I'm just multiplying my radicants together. That's 6 root 36. Square root of 12 times 4. Can't do anything there, but just write that as 4 root 12. Right? You multiply coefficients together and you multiply radicants together. Otherwise, you just show that that's a multiplication by writing them next to each other with no sign. Multiplying my negative 9 root 10 by the 6 root 3, I have minus 54 root 30, and negative 9 root 10 times positive 4, I have minus 36 root 10. In the denominator, 6 root 3 times 6 root 3, I have 36 root 9. 6 root 3 times 4, I've got plus 24 root 3. Negative 4 times 6 root 3 is minus 24 root 3. And negative 4 times positive 4 is minus 16. Okay? In the denominator, my inner and outer added to opposites, so those add to 0. This is just 16. This is not the square root of 16, so there's nothing to do there. Square root of 9 is 3, and 36 times 3 is 108. So I've got 108 minus 16, which is 92. So we have in the denominator 92. In the numerator, going through doing simplification of all my radicals, the square root of 36 is 6, and 6 times 6 is 36. 12 is divisible by the perfect square 4, so that's the square root of 4 times the square root of 3, which is 2 root 3. So we've got 4 times 2 root 3, so this term is 8 root 3. 30 isn't divisible by any perfect square, so I can't do anything with this. And 10's not, so I can't do anything with that. So I have 36 plus 8 root 3 minus 54 root 30 minus 36 root 10. So all of my radicals are simplified. I've got no root in the bottom. But then I have to look at all of my coefficients. 36, 8, 54, 36, 92. They're all even, so they're definitely all divisible by 2. We can start there. If there's more simplification to do, we will. But, start small. Don't try to overwhelm yourself. So they're all divisible by 2. So 36 divided by 2 is 18. 8 divided by 2 is 4. 54 divided by 2 is 27. 36 divided by 2 is 18. And 92 divided by 2 is, 46? Okay. So then looking at them, they're 27's not even, so they're not all divisible by 2 anymore. The only numbers that 4 is divisible by, 4 is only divisible by 1, 2, and 4. So this would only be something I could reduce if all were divisible by any of those 3, other than 1, I guess, any of the 2. So we're completely simplified. We can't do anything else. So we have 18 plus 4 root 3 minus 27 root 30 minus 18 root 10 all over 46. So this meets all 3 conditions. All the roots are simplified, the fraction itself is simplified, and no roots in the bottom. So that's when I know I can stop. So, as you might guess, there are lots of places for you to mess up, lots of places to make small errors. So it's very important that when you're doing the rationalizing that you're cautious in your work, thoughtful in your work, and you have to know those 3 conditions in order to know when to stop. So please let me know if you have questions. Good luck!